All right, so this is Math466, lecture 25. The goal today is to talk about combinatorics and some generalizations of the Fibonacci numbers. So we have two experts on both Fibonacci numbers, and they were working on the 6 case beforehand. So we proved in the last class that if there's any crossing in the 4 case, there's no contribution, and if there are no crossings, there is a contribution. Unfortunately, there's really not that many ways to match things with 4. You know, we can match like this, we can match like this, we can match like this. And so we can conjecture based on this, but we're conjecturing based on a really small set. Now what's nice is the number of possible configurations gets very large. If we have 2m objects, it's 2m minus 1 double factorial. So for 6, it's going to be 5 double factorial or 15, which the kids worked on during complex today and got it right. For 8, it's 7 double factorial, which is 105. You can do 9 double factorial. What's 9 times 105? Well, that's okay. Let's see if you can do it. You should do 9 times 105 isn't too bad.
Oh, wait.
Yes?
945.
945. Excellent, Kayla. So 945 things. It gets really bad fast. All right? But if we write this as 1 and 2, well, it's going to be 11 double factorial. So it's 11 times 945. So it would be 945 plus 945 shifting. So it would be 5, 9, 13. Yes. So it gets bad fast. But if you look at it like this, there are 2 equivalence classes. This equivalence class counts twice. This equivalence class counts once. So the kids have done the next one for 6. Okay. Do you want to do them on the board, Kayla or Cam, or do you want me? Okay. Okay. It's going to be a friendly, informal class. All right. So Cam, you get to do your first one. Or you want to draw them and Kayla will put the numbers on?
No. Sure.
Or Kayla, you draw the last one, Kayla.
I'm going to draw it.
Okay. All right, but see, that's poorly drawn.
Okay.
Right?
I know, I'm a very good artist.
But, you know, again, they should, that's okay. That's better. See, it should be more from like over here. Okay. That's better. Okay. Okay, so that's one configuration for 6. That's another configuration for 6.
Appears 3 times.
That one appears 3 times. That appears once.
Okay, my turn.
All right, now Cam will do the next one. Okay.
This one appears 6 times.
Yep. All right, Kayla's turn. Well, you use this paper, right? So good. And how many times does that occur? Twice. And now we have 1 left. Good. And how many times does that occur?
3.
Okay, good. All right. So these, thank you. These are the 5 configurations and how often each one occurs. So why does this one only occur once? Well, if I rotate it or flip it, it's going to look the same. Basically, everything is matched with its opposite.
What if I drew the lines like on either, so like...
No, we're not. No. What about this? How can you quickly look at it and say there's 3 things that will be configured like this? You can do over there as long as you're quiet. But you have to be quiet. How can you tell that there should be 3 things that have this configuration pattern? So the configuration pattern for this one is the following. It's this. So I say basically by rotating and flipping. So one way to look at it is I match 2 things that are opposite. And once I match the 2 things that are opposite, then I just have to go across. How many ways are there to choose 2 things that are opposite? 3. And that's where the 3 comes from here. Over here, why are there 6 ways to do that? There's 6 sets of adjacent pairs. You know, give the pairs names. You know, Alice, Bob, Charlie, Denise, Ethelbert, and Frankfurt. Okay? You could do Evan, but Ethelbert is just such a nicer name to say. Okay? You have to match a pair. You can match Alice and Bob. You can match Bob and Charlie. You can match Charlie and Denise. So there's 6 ways to choose a pair. What about this one? Well, it's the same argument for this one as this one. You choose a diagonal, and then once you've chosen the diagonal, then everything else is forced. What about this one? Well, you match with one of your neighbors. And once I match this one with its neighbor, then everything else is fixed, or I can go in the other direction. So while there are 15 possibilities, what's nice is by doing this analysis, we've now reduced it to just 5 cases, and now they each have a weight. So all we have to do is find out what is the contribution of each one of these, and then put in the weight. So for those of you who get bored during today's lecture, there are some printouts where you can actually work and try to do these. They're also really good to do if you have an English class later today. Which cases do you think are going to contribute? Which one? The first and the last. So what's good about the first and the last? They have no crossings. So if our no crossing conjecture is correct, these should be the ones that should contribute fully, and then anything with a cross should contribute less. And then this leads to the natural question, how many ways are there with a cross? Or conversely, how many ways are there without a cross? If you can calculate one, you can get the other. This is one of the basic ideas from probability. Sometimes it's easy to calculate the probability of the complementary event and then say, well, then the event you care about is just 1 minus that. So here, let's try to see about these contributions. Do you want to do the first or the last first? You want to do the first last or the last? First first? Last last? So let's say we have this configuration. So here we have L1, L2, L2, L3, L3, L4, L4, L5, L5, L6, L6, L1. When we look at this, L1 and L2 are free. What must be true about L6? So L1 and L2 are free. What's true about L6? It's fixed. In fact, L6 has to equal L2. Now we know L6. L5 equals L5. What do we know about L4? Fixed. And what does L4 equal? L6, which is L2. And now we add L5 as something that's free. And now we come over here. L4 is fixed. L4 equals L2. Phew, good. It works. It's consistent. And L3 is free. So we have 4 free variables, and they can all go from 1 to n. And then we have 2 fixed variables. And so the contribution should be 1 over 2 to the, okay, so here k is equal to 6, k halves will equal 3. So we'll have 1 over 2 to the k, which is 1 over 2 to the 6th. Then we have n to the k halves plus 1, so that'll be n to the 4th. And then we have n to the 4 tuples. And each tuple, we're going to get a second moment squared. We're going to get second moment 1 times 1 times 1. There's only one small issue. This is slightly wrong. And the reason it's slightly wrong is I said L5 and L3 are free. Well, here, we have an L6 here, which is the same as L2. We have L5. What if L5 equaled L1? Then this value would be the same value as that, and it would be a quadruple. So is L5 free? It has n minus 1 degrees of freedom. So we will see if you guys are better culturally than Math466. They failed today in pop culture. That's bad. Best romantic comedy of all time.
You have to narrow it down.
With pirates. And people avenging their fathers. Princess Bride? right, how many of you have seen Princess Bride? When they take, this is disgraceful. This is disgraceful, okay? You should watch it. I will loan it to people if necessary. I will have a movie night and show it if necessary with pizza. It's a movie you should see before you graduate. All right, so for those of you who have seen it, this is your chance. When the Dread Pirate Roberts is brought to Miracle Max, what is his condition? No, yeah, you were in 372 earlier today, Kim. You may not speak. Yes, you were. He is not dead. You can say it. He's mostly dead. Right. Remember, all dead, you can't do anything except pick the pockets looking for loose change. But mostly dead means somewhat alive. Yeah. Okay? This is really what's going on here. If you want, you can think about this as the Princess Bride view of combinatorics. Is L5 free? Mostly. It's mostly free. So these two are really mostly free. And so what you really have is you don't have n to the fourth. What you really have is you have n from L1, n from L2, n minus 1 from L5, and what is L3 going to be? N minus 2. And so the main term is going to be of size n to the fourth over n to the fourth. Great. And then you'll have a lower order term of size 1 over n. So you'll have some idea of convergence rates. So this will contribute fully. So it's a full contribution. Okay. It'll just go to 0, exactly. But this will give you an idea of how rapidly the average moment is converging. Okay? Because in those cases when these are the same, you're not going to get the second moment 3 times. You'll get maybe the second moment once and a fourth moment, or you might even get a sixth moment. Okay? Okay, so this handles this case. Now we have to handle the other case. All right, can I erase this? Or are you people still writing? Okay, so now the next case was the other one. And so you can see that for our cases, free and mostly free are effectively the same. The other one was case 3. So do you think this is going to contribute fully or not fully? So this is L1, L2, L3, L4, L4, L5, L5, L6, L1, 2, oh, sorry, L2, L3, L3, L4, L4, L5, L5, L6, L6, L1. So before we do the calculation, what do you think? Full contribution or not full? Not full? All right, how many people say not full? So we've got 2 not fulls. How many say full? 1 full and 2 abstentions. We've got 2 undecideds. All right, let's go through. We start off with L1 and L2 as free. Now we come over here. L3 is the same. L2 was already determined. What's true about L4? L2. So L4 equals L2. Now we come down here. Is L5 free or not free? L5 has to be L1 because we'll see. L4 is equal to L2. Good, that matches up there, so it's consistent. And then L5 has to be L1. So it's a little bit different than last time in terms of what the fixed things are. Okay? Now we come over here. We have L5 and L6. Well, L6 is the same, so this tells us L5 has to be L1. Oh, good, we already had that. So L6 is free. And we forgot to write down that L3 was free. And now we have L6 is free. And so again, it should be a full contribution. And again, what's true about L3 and L6? Kind of, no, we don't say kind of, mostly free. Somewhat free, mostly free. And this will again be a full contribution. Now the harder part is to show that once there's a crossing, there's going to be a decrease in contribution. Okay, so I'm going to put that on hold for now. That's a very nice penguin and a nice ball field. Put in the scoreboard the Red Sox beating the Yankees, please. Okay. Excellent. All right. So do we agree that this isn't too bad? And what's nice is you can check that this sums to 15. So we must have found everything because there's 15 ways to match. You can also go through by brute force, and I've provided some paper. Now, if you want to do 8, how many ways are there to do 8? 105. How many different congruence classes are there? Just before I started teaching at Ohio State, I was at the American Institute of Mathematics, and I was working with a summer research student. There's 7 distinct classes? I think it's more than 7. Yes. And so I was working with a summer research student on Toeplitz matrices, where the matrices are constant along diagonals. And we needed to know how many ways there were to do 8 and what was the contribution from each one of them. And so we broke it in half. I did half, he did half. When I went to Ohio State, I worked with a student and we wrote down all the configurations for 10. And just how many times does each one come? You really want to do this almost by induction. And let me put in a cross and see. So let's count how many ways there are to have no crosses. And then it turns out it's not going to be hard to show that if there are no crosses, it contributes fully. So counting no crosses. So one of the things I like about this subject is it shows you how math is interconnected. I'm doing a problem in analysis and probability, and it actually turns out to be combinatorics. It comes down to how many ways can you count something happening. It is a sequence which you have seen before. I know we did it briefly in probability. If you haven't taken probability, you might have seen it if you've gone to Budapest. It's a very famous sequence. So I want to count how many ways there are to have things without crossings. So we'll have an even number of objects. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I have to match things in pairs. How many ways are there to match 12 objects in pairs without crossings? This is a painful problem. So what we're going to do is we're going to start off with a special point. Without loss of generality, well, that's when you put like a little flag. Okay, here's my special point. It has to be matched with something. You actually know something about where it must be matched. So you should be able to tell me one place where it cannot be matched.
You can't do it to like one of the third one.
Right.
Because then there's 2 will cross.
Right. I can't match it with 3, because if I match it with 3, then 2's got to go somewhere. Okay. Could I match it with 4? Yes. Could I match it with 5? Because if I match it with 5, right, either one of them crosses the line, or if they all stay inside the line, one is left over. So again, this is a really nice odd-even argument. If everything is matched in pairs, if I match this with an odd number, I'm in trouble. So how many places can I match this with? M minus 1. There's 2m dots, so there are m numbers of the same parity, and you cannot self-match. So you have m minus 1 choices. So let's say we match it somewhere. We match it over here at 2l plus 1. Okay? And so now the question becomes, how many ways can we match these objects in pairs and these objects in pairs? So here, actually, so I want to match with the opposite pattern. So let me do it like this, so at least the drawing looks good. How many ways can I match these 4 objects in pairs without crossing?
Shouldn't it be matching with 2L because it has to match with 9?
Oh, sorry, yeah, I'm sorry. It should be 2L, yes.
Couldn't you define like a function and then do it recursively? Like
Yeah. So let's let C of 2m equal the number of ways to match 2m objects in pairs without crossing. I'm sorry?
There's something wrong with it.
I thought I moved an extra dot here.
Well, there's like,
Oh, all right.
yeah, there's not enough dots.
Sure. This should be like dot, 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 but sure.
Yeah.
Yeah. Anybody know why I'm using the letter C? It is not because of guests today. I would never choose just C in a case like this. This would be bad. It's related to a very famous sequence of numbers that has a combinatorial interpretation.
Cauchy?
Nope, not Cauchy. So how many ways are there to match these four objects in pairs without having a cross? Yes, Kayla? Are you stretching? There's two. I can match 2 and 3 and 4 and 5, or I can match 2 and 5 and 3 and 4.
Yeah.
So there are two ways to do that. But that would have a cross. I don't want crosses right now.
5 and 3 and 4 and 2.
Well, but if I do 5 and 3 and 4 and 2, then there's going to be a cross. And right now I want to look at how many ways to do it without having a cross. So now if you look at it, we have C4 ways to do this. How many ways do we have over here? This is where you have to play the index game. So how many dots would I have here? If I have 4 here and 2 more here,
2m minus 6.
so I have 2m minus 6. So it'd be C of 2m minus 6. So how many ways are there to choose a matching here and a matching here? I'm sorry? You'd multiply them, right? Because they're two independent choices. Once I make this cross, I have C4 ways of doing this, C 2m minus 6 ways of doing that. Now in general, if I have 2L here, then how many elements do I have in here? 2L minus 2. So this would be C of 2L minus 2. And over here, what would this be?
C of 2m minus 2l minus 2. Yeah.
I'm not sure if that's right. I don't think there's a minus 2.
2 minus 2l.
It's just C 2m minus 2L.
Yeah.
That's fine. No. The probability of making an index mistake here is about 105%. It's high. You know that this plus 2 must equal 2m. So that's a quick check. If this is 2l minus 2 and this is 2, that gives me 2l. So I have 2m minus 2l objects left. So we get this beautiful recurrence relation. C2m is equal to the sum, L goes from something to something, of C2L minus 2 times C2m minus 2L. Okay? So all we have to do now is figure out what's the range for L. So what are the possibilities for L?
All the even numbers.
You can't use go like.
Remember, I'm matching my point 1 with the point 2L.
1 to 1.
1 to m.
Yeah. Then there's something. Maybe 0 comes in there where it's this one.
Well, no, because so if L equals 1, I've just matched it with 2.
Right. So it's
If L equals m, I've matched it with.
and we're defining.
Oh, wait a minute. We've got to be careful.
No,
This point,
C0.
this point is 2m. This point is 2m, not 2m minus 1.
Okay. So if we define C0 equals 1, then
Yep.
we're fine.
Yep. And so this is very similar to now what should 0 factorial be? So what should C0 be? How many ways should there be to match 0 objects in pairs without crossings? 1. There's one way to do nothing. Or should it be 0? Well, let's check. We know what C4 is, right? What is C4? How many ways are there to match two objects in pairs without crossings? So C4 equals 2. So let's take m equals 2. If we take m equals 2, we get C4 is equal, L goes from 1 to m. So when L equals 1, we get C0, C4, plus, then when L equals 1, when L equals 1, wait, when L equals 2, we get C2 times C2. No, times C0. That's right. Oh, wait, when L equals 1, we get C0, C2. And then the other one we get C2, C0. Right?
Yeah.
And we know C4 equals 2, C2 equals 1. So what does C0 have to be? So we have to define C0 to be 1. So as you would expect, there is one way to do nothing. Okay? Should we check one more? Should we check what C6 is? C6, so it should be, well, we have indices that have to add up to 6. So the first one, when we take L equals 1, we'll get C0. Oh, no, I'm sorry. The indices add up to not 6, they add up to 4. So we get C0, C4, plus C2, C2, plus C4, C0. Right? C4 is 2, right? So that's 2. What's C2 times C2? 1. So we get 2 plus 1 plus 2 is 5. Is that correct? That's what we did before. Remember we had, or is this correct? So when we go back to our pages before, how many ways do we have to do each? We had 3 for one and 2 for the other. Was that right? Or was it 3 and 3? No, it was 3 and 2, right? When we did the case of C4, this way, there were 3 ways of doing this. And the one that was like this, there were 2 ways of doing that. So we get C6 equals 5. And that's exactly what we get here. That's a good sign. So now we can actually answer that question we had a moment ago. How many ways are there to do 8? So this was what I gave Kim and Kayla, and I said they could have, I think, like 5 candy bars each if they got this. You didn't get 8. I'll check later. If you're right, I'll give you the candy later. So C8 should be C2, and then it's got to add up to 6, so it should be C2, I'm sorry, C0, C6, plus C2, C4, right? Plus C4, C2, plus C6, C0. All right, C6 was 5, and C0 is 1. C2 was 1, and C4 was 2. So the next one is 2. C4, C2 is also 5. So is also 2. And then C6, C0 is 5. So there's 14 possibilities. If we do C10, it would be C0, C8, plus C2, C6, plus C4, C4, plus C6, C2, plus C8, C0. So C8 was 14. So we have 14. C2 times C6. C6 was 5, is 5. C4 times C4 is, C4 is 4. And then this was 5, and this is 14. So 10, 20, 30, 42.
63.
42, right?
Yeah.
Okay. So our sequence is 1 for C0, 1 for C2, 2 for C4, 5 for C6, 14, and then 42. Does anybody recognize that sequence? 1, 1, 2, 5, 14, 42. What should you do for the sequence? I don't know if I've ever mentioned this in this class, but I have mentioned this in other classes. Look on the online encyclopedia of integer sequences, right? If you feed this in, and so I coincidentally have a computer that's already loaded. Okay, so I'm going to enter the first few terms. 1, 1, 2, 5, 14, 42. And the number of terms it finds, it's calculating, it found 58 results. It's a lot. So we need to do a few more terms to have it narrowed down. Now, fortunately, the very first one that it displays is the right answer. These are the Catalan numbers. And that's where C is. So the other interpretation of the Catalan numbers is the number of ways you can walk from the bottom left to the top right without crossing the main diagonal. So, here's what we have. 1, 2, 3, 4. And I want to know, I have, n moves going to the right. I have n moves going up. How many ways can I walk from the bottom left to the upper right without crossing the main diagonal? How many total paths are there where I don't care if I cross the main diagonal? So how many ways could I do it if I don't care if I cross the main diagonal? How many steps do I have to take?
How many ways I could do it?
How many ways can I walk from the bottom left to the upper right, doing n rights, n ups, and I don't care if I cross the main diagonal or not?
2 to the end.
Yes. So there's 14 equivalences I think we've determined. Put it over here. So how many paths are there from the bottom left to the upper right? I've got to take n rights and n ups. How many ways are there to order those steps?
N factorial divided by like n over 2 factorial, n over 2.
Almost.
2n factorial.
2n factorial over n factorial, n factorial. It's just 2n choose n. How many ways are there? Well, I have 2n objects, and n of them are identifiable and are the rights. I choose n of the 2n steps to be rights, and then all the other steps are ups. So this is how many paths from here to here. It turns out that if you stay below the main diagonal, not surprisingly, you lose a bunch of paths, but not a huge number. It's still going to be exponentially large. So why is this the same as this problem? What you can do is let's look at the first time. Let's see. So I'll just sketch it. If I have this point here, and I walk and I stay on the main diagonal or below, there's got to be a first time it returns to the main diagonal. And the first time could be here or here or here or here. And then we know we have to end here. So I'm not going to do things fully rigorously, But I could say, well, look, I can take some path until here, which is valid, and then some path from here, and then all the ways I can do things here times all the ways I can do things here. You've got to be a little bit careful because you're talking about the first time I return. Well, if it's the first time I return, then I've got to be like this, and I have a legal path along here. Or if the first return maybe better was all the way over here, I would have to be in this part of the triangle. I would start here going to the right, then do something in through here, and then come up. And that's how that could be the very first return. And that's how I'd then be piecing things together. And so what you would notice is then I have a Catalan path from here to here. And if I do things by first return, the paths will be distinct. And then over here, this is a Catalan number as well. It's just all the paths from here to here. I don't care if there's any returns or whatnot, because this is below the main diagonal. So what you would basically get is, up to some index errors, which I don't care about, is, Cn would be over here. I've lost one move. And I choose where I want to go. So it'd be something like a Catalan number on L minus 1. And then over here, I would times like a Catalan number of like n minus L. And I'm not even worrying right now about getting my indices right. It's something like this. This is made smaller because this move has to be fixed to the right. This move has to be fixed to the up. And then it's a Catalan number of one smaller size. And then over here, this is a Catalan of what's left over. So it should have added up to n. It adds up to n minus 1. And then L could go from 1 all the way up to, I think, n. And that's essentially the same recurrence we have. Because everything here is even, we might as well just drop all the 2's.
Sorry, is that the Catalan number? So Cn L minus 1, Cn n minus L, or n minus 1?
This is n minus L. Is, if this is of size L over here, then we have n minus L points up here. And we've lost one unit because of how we have to go. So really what you want to do is you want to replace all the numbers here with halves. Because we're just doing everything on the evens, so let's just make our life easier. So what I'm hoping you're seeing from this is that we have the same recurrence.
Why can't you go like all the way to the right?
You could.
Left?
You could.
You can't go left.
You can't go, you mean up.
Oh, you can't go left.
You can't go left. It's only rights and lefts. Yes. It's like lower triangular matrices. We don't allow motion like that. Okay. You could go all the way to the right and then all the way straight up. And then that would count in the case when L equals n. And you're now basically just doing your lower Catalan number down in there. It's the same relation. Notice that this is a much worse relation than the Fibonacci's. The Fibonacci's is fn plus 1 is fn plus fn minus 1. Right? So the Fibonacci's is a much nicer relation. It has two terms. It always has two terms. And the coefficients of the two terms are 1. And the terms are additive. Here, the length of the recurrence grows. That's painful. And it's a quadratic recurrence where you multiply them by each other.
Is that a closed formula there?
Of course. Well, I mean, I've told you what the closed formula is. It's 2n plus 1 over n. So there is a closed formula. So the question is, how do you find the closed form? Yes. 2n choose n over 1 over n plus 1. If I give you this, if you have been divinely inspired, how would you try to prove this now? Induction. So as a nice exercise, if there was homework, prove by induction that this is the formula for Catalan numbers. Is divine inspiration a valid way to prove things?
In your classes.
In my classes, yes. On exams, however, it can be fickle. And you cannot always count on being divinely inspired on an exam. So the question is, how can we prove this? So I'm going to change our relation and just divide everything by 2. So let's say Cn is equal to the sum. L goes from 1 to Or do I want to do it like this? Maybe n halves of C L minus 1 C n minus L. All right. So this is the recurrence I want to do. Okay? So we're going to use generating functions. So I know if you've taken probability with me, you've seen generating functions. I think we did generating functions for Fibonacci's in this class. So what we're going to do is we're going to define a function, f of x, to be the sum, n goes from 0 to infinity, of Cn x to the n. Now, at first, this seems like a very stupid thing to do, because we don't know what the Cn's are, and we're building a function where these are the coefficients. I want to get a product of things. If I have another function, g of x is the sum n goes from 0 to infinity of, say, bn x to the n, I could ask, well, what happens if I multiply them? And so if I look at f of x times g of x, that's the sum n goes from 0 to infinity of Cn x to the n, sum, I'll use a different letter, m goes from 0 to infinity of bn x to the m. So what I can do is I can multiply things out. This will be c0 plus c1x plus c2x squared plus yada, yada, yada. b0 plus b1x plus b2x squared plus yada, yada, yada.
The x in your b should be m, right?
It should be m, yes, thank you. And so now when I multiply things out, I'll get c0 b0 as the constant term. For the x term, I'll get c1 b0 plus c0 b1 x. The x squared term will be a c2 b0 plus a c1 b1 plus a c0 b2. And in general, ck b0 plus ck minus 1 b1 all the way down to c0 bk x to the k. So notice that this is essentially what I want. Right? I want to get cl minus 1, cn minus 1. That's almost what I have here. So it's going to come down to just algebra and whatnot. With 5 minutes, there's about an 80% chance there'll be an algebra mistake, which will prevent it from working out at the last moment. But it'll be close. So what do you think we should take for our sequence of b's? Also the Catalan numbers. So let's look at f of x squared. That will be the sum, n goes from 0 to infinity. So now we'll get c, I'm starting it with the 0, so it'll be c0 cn plus c1 cn minus 1 all the way down to plus cn c0 x to the n. Okay, what does this look like? Well, we know that cn is the sum, L goes from 1 to n halves of cl minus 1, cn minus 1. Let's just shift the L summation.
N minus 1 or n minus L? It's really close. But
N minus L, thank you.
slightly off.
But look, if I just shift, if I replace L with K, if I let L minus 1 equal K, this is now a sum. K goes from 0 to n halves minus 1 of CK, C, n. Now I have to add 1.
Minus k plus 1.
So I think it's n minus 1 plus 1 because I need the minus sign here. So it's n minus 1 minus k. So Cn is this sum. Or another way of saying this is Cn plus 1 is the sum of k goes from 0 to n halves, I guess maybe n plus 1 minus 1 of ck Cn minus k. So these numbers here should basically just be Cn plus 1. So what we should get is we should get f of x squared should be the sum, n goes from 0 to infinity, if I haven't done any mistakes, Cn plus 1 x to the n. So now f of x squared is the sum, n goes from 0 to infinity, Cn plus 1 x to the n plus 1. Just multiply both sides by x. F of x squared, this is almost f of x. It differs from f of x by c0. And c0 was 1. So this is just f of x minus 1. So we get f of x squared minus f of x plus 1 equals 0. I'm going to be close. It depends on how accurate the clocks are. Oh, well, 3 minutes, yes. Excellent. So now we have to solve this. How do we solve f of x squared minus f of x plus 1 equals 0? How would we solve this? Come on, you got to figure it out fast. We don't have much time. Quadratic formula. So you get f of x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And now all we need to do is expand this out and we'll get the Catalan numbers. Ooh, we have to expand out a square root. Yay, we get to use the generalized binomial theorem. Normally we use the binomial theorem if it's an integer power. Now we need Newton's refinement. Now there's one part that might worry you a little bit. What might worry you a little bit about this? You can have imaginary numbers, you can have 0, but it's that you have 2 solutions. We're a little short on time, so I'm going to call on myself. We should only have one solution. Well, we know earlier, we know that c of n is less than or equal to 2 to the n, 2n choose n. This is less than or equal to 1 plus 1 to the n. It's less than or equal to 2 to the n. So we know f of x converges if the absolute value of x is less than 1 over 2 to the n, because it'll be a geometric series. So f of 0 should be well behaved. If I send x to 0, I want to make sure that this is well behaved. So as x goes to 0, this is going to look like the square root of 1. I'm dividing by x. Which root do you think I want, the positive or the negative? The negative. The positive root blows up. So it's got to be f of x is 1 minus the square root of 1 minus 4x over 2x. Oh, I'm sorry, this is to the 2n, sorry. So it's 2 to the 2n, so it's 1 over 4 to the n. And look at this, we have a 4 over here. That, you can tell this is going to be making sense for x up to about 1/4. When x is greater than 1/4, you're going to have the square root of a negative number. So everything is nice and consistent. Okay? Now all that is left is expanding the square root. And if we expand the square root, then we're done. So you just need Newton's generalized binomial formula. So I will leave that as an exercise, but use Newton's generalized binomial formula to expand the square root of 1 minus 4x. And so if there was homework for this class, this would be a great homework problem. And you can actually start taking derivatives. You'll notice a pattern. Factorials will come into play. And by doing some algebra, you will get the 2n choose n divided by n plus 1. And so what I wanted you to see in today's lecture is, again, the interconnectedness of mathematics. That we had a problem in analysis. We reduced it to a problem in combinatorics. We got a recurrence relation. When you can get recurrence relations, if you can solve them, you're in great shape. But the problem is, how do you solve this? This was a harder one. The recurrence relation was not a finite depth. It was not with constant coefficients. But we had a way to solve it with generating functions. Generating functions is one of the most powerful techniques we have in the semester. In the